I want to talk about this evening is something that has arisen out of the field of pulsar research, which I have been following for most of my adult life. It's a brand new topic called fast radio bursts, and it seems to me to be one of the most exciting developments in astronomy, astrophysics at the moment. A little bit of recapping. I'm going to be talking almost exclusively about a topic within radio astronomy. So a quick reminder here about the electromagnetic spectrum, tiny little bit in the middle that our eyes can see, out the violet side of the rainbow, ultraviolet, X-rays, gamma rays, out the red side, infrared, millimeter radio. We now know that stars and galaxies radiate right across that whole lot, and not each one of them over all of it, but between them. You can do astronomy at any of those wavelengths. So I'm going to be focusing particularly on radio astronomy, which developed post-World War II when radar boffins, as they were inevitably called, returned home and used the receiving techniques from radar, not the transmitting, just the receiving, to look at the sky and found many, many fascinating things. So you're probably well aware of radio telescopes. One of the early ones is at Jodrell Bank in the United Kingdom. The US's biggest one is in Puerto Rico, the Arecibo radio telescope, at least the biggest single dish. There's another very large one in New Mexico called the VLA, or the Very Large Array. A little bit of physics for those who are not physicists. I need to be able to explain what we can do by studying dispersion. Dispersion is what you get, for example, when light shines through a raindrop or when light shines through a glass prism. You get white light split out into its constituent colors. The different colors have different wavelengths or different frequencies and travel in slightly different paths through the raindrop or the prism. There is a radio equivalent of this, and it first came to light, people doing audio studies, electromagnetic studies of the near-Earth environment, and they picked up something that they named a whistler. We're about to hear an audio recording. This may give you advance warning. There's a lot of static on this recording. You're listening for a signal that starts at a high frequency and drops in note. Only it probably won't be that clear. Now, what has happened is on the other side of the Earth, there's been a lightning flash. The lightning flash generates a very sharp radio pulse that contains all the possible radio frequencies. And this radio signal sets off towards us in the northern hemisphere. It's guided round by the magnetic field lines and travels through space that's fairly empty, but not completely empty. There are some free electrons in that space. And free electrons affect radio waves the way glass and raindrops affect light rays. It separates out the constituent frequencies. So what we hear arriving after that journey is not the but the component frequencies arriving one after the other, starting with the highest frequencies and descending. So you get this descending whistle. Radio astronomers make use of this regularly. The one other bit of information I need to give you is how quickly this descends depends on how many free electrons the radio wave has come past. So if it's made a short journey, the track would be a lot steeper. If it had made a longer journey, it would have been a lot more spread out. So with that bit of information, question for you. Can anybody tell me where this one has come from or where this one has come from? Have they come a long way? No, they're local. These are locally generated interference signals. Your mobile phone, your digital camera, sometimes microwave ovens can generate interference signals, and they'd show up on these as vertical lines. So that's dispersion. And I now turn briefly to pulsars. A cartoon of a pulsar, a tiny star spinning quite rapidly, a pair of radio beams probably coming out from the magnetic poles and sweeping round the sky like a lighthouse beam. If the beam shines in our face, we get a pulse, like now. The other beam misses us, now. Misses, now. And they come round very, very regularly because this is a surprisingly massive star with a large moment of inertia. Those radio pulses from a pulsar are traveling through space to reach us on the Earth. And one of the issues we have when we're studying pulsars is we see a flash. Is it a pulsar or is it locally generated interference from your digital camera or your mobile phone? So routinely, the radio astronomers make this kind of plot where the different frequencies are plotted against time, and you get this same descending whistle type of note. That means it's come a long way. If this were vertical, it would say that spike was a blast of local interference. And furthermore, pulsar astronomers can tell from how fast this is descending how far away the pulsar is. And that's absolutely routine. They always do these plots because it's a superb way of distinguishing between a pulse that's local interference and a pulse that is a pulsar. So, when a radio astronomer saw this kind of plot, here's the nice pulse, here's the descending signal, they said, great, pulsar. And then they stopped and they looked at how slowly this was descending. And it's going extremely slowly, so there's an awful lot of electrons between us and that source. So how far away is it? All the pulsars we've seen so far are in our galaxy, so we've got a good measure of how many electrons there are in any direction in our galaxy. And in the direction of this thing, let's say it's straight down the aisle, in the direction of this thing, there aren't enough electrons in our galaxy to explain that slow descent. You need a lot more electrons. So it has to be beyond the galaxy. The snag is when you get to the edge of the galaxy, the electron density drops like a stone because you've reached the edge of the galaxy. You're in intergalactic space where there are some electrons, but they're not nearly so common. And so to explain the remaining number of electrons to get that slowly descending whistle, you have to go miles and miles and miles. Okay, this thing, whatever it is maybe in another galaxy, and that other galaxy, that host galaxy, will give you some electrons, but it's still in a very distant galaxy. And while we just had one of these, it was a big question mark. We checked with other astronomers whether there was any optical emission, X-ray emission, what have you, in that direction. No, nothing doing. So ultimately, Duncan Lorimer of Virginia, West Virginia, decided to publish this. It was still the only one known, but he couldn't find anything wrong with the logic, the detection, the equipment, so he published. And for a long time, it remained the only one. And then we started finding more. It was always the pulsar astronomers who found them, because it's always the pulsar astronomers who are looking for quite short pulses and are checking the dispersion. Most of the pulsars we've discovered by chance. We now have about 70 discrete sources all around the sky. With one exception, they never repeat. The one exception turns out to be useful because it does repeat, and you can go back and get some more pulses from it and do some more studies. And it turns out to be in a galaxy quite a long way off. And that's consistent with these other ones, these single ones, which also are at considerable distance, way, way beyond the galaxy, at what we call redshifts of 0.5 or 1. At last, we've done a survey, just one survey, only published about a week ago, and they found a number more, and they're now able to say that by and large, the brighter ones are nearer. No great surprise there, that makes sense, but good to know. And we're still not much closer knowing what they are. The whistle very, very accurately follows the frequency dependence we expect. Frequency to the minus 2.000, pretty good. And some of them have this little scattering tail due to blobby stuff in the interstellar medium. It goes as the frequency to the fourth. That works. It all fits together. But we still don't know what they are. The repeater, the one repeater, we now suspect is something slightly different. But for the record, it's coming from a galaxy. We managed to get some optical detections at the same time. It's a tiny galaxy. It's a dwarf galaxy. Dwarf galaxies are 2 a penny. It's not even the center of the dwarf galaxy. Star-forming region in a dwarf galaxy. There must be zillions of those in the universe. What's going on? Somebody's applied deep machine learning to the data taken from that bit of the sky and found a lot more fainter pulses, so it is doing a lot of repeating. We still don't know what it is, but we're beginning to suspect it's different from the other 69 or so that we know about. A cautionary tale. The Parkes Radio Telescope in Australia was picking up a number of these bursts, and another category of burst that didn't seem quite the same and was a little bit puzzling because they all seemed to be at about roughly the same direction, the same distance, but in all sorts of directions. And they weren't at all sure what was going on until a grad student did a very interesting plot. This is a plot of the number of bursts against local time, time of day, human day. And there's a peak between 12 and 1. What do we do between 12 and 1, folks? We have lunch. We microwave. They have had a microwave oven or 2 on site. They had checked them very carefully that they didn't leak and give radio interference, so they thought it was okay. But listen up, because this affects you. If you stop a microwave oven by opening the door, it doesn't stop immediately. There's a short burst of microwaves, which you get in the chest, and the radio telescope picks up as a fast burst. And all these bursters were at the same distance because a microwave oven's job is to turn water molecules in the form of ice into molecules in water, into molecules in steam. That's how it heats the food. And a water molecule in ice vibrates at a slightly higher frequency than one in water, than one in steam. So the microwave scans down. And it happens to use a scan pattern which mimics the 1 over f squared. But please, in future, maybe you do it already, stop your microwave oven by pressing the stop button. And congratulations to the grad student who thought to do that plot. they now no longer have microwave ovens on the radio astronomy site. And the staff are unhappy because the convection ovens don't work so fast, but however. So where's all this going? Up till now, we have picked up these bursts by happenstance. We were doing pulsar observations, and oh, there's a burst, and it's sort of somewhere in that direction. The Canadians have a very new radio telescope in British Columbia, near Penticton, for those who follow radio astronomy. And you can see it in this slide. It's called CHIME. It was designed to do work on hydrogen in the distant universe, but it's been adapted in a minor way, and it's now good for picking up these bursts. And it has already seen a few bursts, and there's a rumor in the network that there's something else very interesting it's seen. Don't know what it is. Don't know if the rumor's accurate, but it could be, because this is going to be one of the best telescopes we have for picking up these bursts. To state the obvious, astronomy, along with geology and archaeology, are observational sciences. You cannot say to the star, please turn up the wick, I want to measure so-and-so. You cannot say to the buried body, can we rerun your burial service because I want to see it? And we can't say to the folded rocks, would you mind going straight and refolding because we want to see it? In astronomy, you can't control nature. You can get better at picking up the pulses and be cleverer in what you do with the photons that nature sends you, but you can't control what nature sends you. But the ways we're moving are, for example, more simultaneous multi-frequency work. There's a newish telescope in South Africa called Meerkat. It's a radio telescope. It will be scanning the sky for transients, amongst other things. They have set up alongside it a little optical observatory with quite a small mirror, which covers the same patch of sky as the radio telescope and is slaved to the radio telescope in the sense that it points where the radio telescope points. So if they pick up a radio burst from there, there'll be an optical telescope looking there, and they'll be able to see if there was a bright optical flash or not. We can also make better use of the radio polarization data, which tells us about magnetic fields. And there are a number of curiosities that we haven't yet resolved. If you look carefully at one of these sweeping plots, this is not showing it very well, but in a number of cases with this sweeping plot, you find that there are bright spots and then gaps and bright spots and gaps and spots as you go down the length of the sweep. And we don't yet know what's causing them. We don't know if they're stable or whether they change. They're probably some kind of plasma effect, but we haven't yet done much work on what those things are. And there's work to be done there still. And clearly, with the developments in machine learning, we can apply machine learning to the data. The one survey that's been done, I think, is asking for machine learning to be applied to that data, particularly if you're looking at the spot where there was once a burst, and there hasn't obviously been one since. Can machine learning fish any out of the murk or not? I don't know. But that'll be quite a good test. It may be that these things are catastrophic events. They're the end of something, and it's been and gone and done it, and there's nothing to be seen subsequently. Certainly, they have observed for something like 1,000 hours the sites of some previous bursts and found nothing. So I find this a hugely exciting and rapidly developing subject. I can't quite fulfill Yuri Milner's brief to say where we'll be in 10 years, but I think you'll understand why. And thank you for your interest.
One thing that you often hear about when people do this kind of astronomical experiments is getting a data point from somewhere else in the world. It seems like you would just, immediately know what the interference was if you had another data point from somewhere else.
Yes, we're not too worried about interference because we're measuring the dispersion. We know these things have come past a hell of a lot of electrons.
No, but I mean just in terms of like the microwave stuff you would have.
Oh yeah. Oh yeah, well, we were telling the Australians that they had a problem, but yeah.
When you look at the optical slave telescope with the radio telescope, what's the resolution of the angular resolution of the radio telescope? Can you tell exactly where it's looking in the optical image?
The optical field of view is exactly the same as the radio field of view and is designed to be such. But the radio telescope is quite a wide field of view, which means the optical is not the optimum for an optical telescope. But if there is a flash in approximately the right place as the radio burst, we'll be pretty happy.
Could you see where in the image, though, that the optical image should be?
Yes, broadly you can see where. Yes, indeed. Yes.
So Jocelyn, the recent success in problems like this is gamma ray bursts, which I remember were equally as mysterious.
Yes.
And there we had the hint from the distribution that they were extragalactic and cosmological, and so even at this point, do we know enough to know a character? I mean, besides the fast repeating one, a characteristic sort of redshift range to be thinking about?
Yes. In fact, we're doing slightly better than the gamma ray burst people, because the first thing the gamma ray burst people were able to say, these things are evenly distributed over the sky, which could mean they were very local or very distant. And it wasn't until they got an optical identification that they could say the very distant option was right. We already know these things must be very distant because of the rate of descent of that whistle and the number of electrons that there have to be. So we're a bit better there. And I've forgotten the rest of your question, sorry. Do you still have the microphone?
Is that enough to give you a characteristic redshift?
Yes, it is. And the ones we've found so far are between a redshift of 0.5 and 1. So we're talking several billion light years, which is quite significant.
Perhaps I didn't follow this closely, but as I understood it, the pulsars you're finding within our galaxy,
Yes.
Why do you think you're not seeing them outside of our galaxy? Are they detectable outside, or do they not occur? What would be your view?
We're pretty certain that pulsars do occur in other galaxies, but just at the moment, soon to change, just at the moment our telescopes aren't sensitive enough to see them beyond our own galaxy. But they ought to be in every galaxy. Yep. Thank you.